Today we're going to discuss the concept of pressure. So as we start talking about gases, pressure is one of those things that allows us to interact with gases. I mean, it's what we feel when gases are in contact with us. So we're going to start with pressure and discuss some of that. So what is it that causes pressure? Well, the main source of pressure is collisions. What we're going to see is that in order to generate pressure, gas molecules have to collide with the surface of whatever container they happen to be in. So you can see that in this model here, the small blue particles are bouncing around, which is what gases do all the time as long as they're above absolute zero. Those gases are going to collide with their container walls. And those container walls are going to exert, or the gases, I should say, are going to exert a force. All right, so if we look at pressure itself, we simply take the force that those particles exert and we divide it by the surface area over which they exert that force. That's going to give us pressure. Okay, so essentially, this is the source of pressure. Those collisions generate gas pressure. And once again, you guys, if you want to pause it, if you're taking some notes and you want to pause it, of course, feel free to go ahead and do that. So how do we measure this pressure? Well, the very first measurements of pressure were primarily measurements of atmospheric pressure, the pressure that the gases that make up the atmosphere press on us with. So there was an Italian fellow named Evangelista Torricelli. He was the first person who created a device that allowed him to measure atmospheric pressure. From your crosswords, you may remember what this is called, this device to measure atmospheric pressure. This device is called a barometer. So we're going to look at barometers in a moment and kind of figure out how they work. But what you may not realize is that if you've ever been in a swimming pool, and I know a lot of times people will get in the pool, and if you have like a plastic cup or something that you're drinking from, you put the plastic cup in the pool and you fill it up with water and then flip it over and then slowly pull it out of the pool, but not all the way. And what you've probably noticed is that the water in the cup doesn't drain out. If it's even the cup's upside down, it's full of water, and you pull it out of the pool, but not all the way out of the pool, the water stays inside the cup. And it almost seems like magic because water, I mean, gravity's pulling down on that water, and it should be causing the water to drain out, but it doesn't. What you've done there, when you flip that cup upside down and then try to pull it out, you made a barometer. Effectively, you made a barometer just like Torricelli did hundreds and hundreds of years ago. I want to say this was late 1600s is when he did this, okay? Now, why would we want to know what the pressure of the atmosphere is? Well, this is a major factor in determining weather conditions. What we see is that generally, if the pressure of the atmosphere is relatively high, we're going to get clear skies, warm temperatures, that kind of thing. The reason is the reason your pressure is high is that air in the atmosphere is sinking when your pressure is high. And that means that instead of the moisture in that air rising up and cooling and then condensing into clouds, when air is sinking, the air heats up. So any water that's in that air stays as gaseous water and doesn't turn to liquid. So that means you're less likely to have clouds, you're less likely to have rainstorms when your pressure is high. On the other hand, if your pressure is relatively low, that means air's rising up away from the surface. And as it rises, it cools. The water that's in it condenses and you make clouds. All right? So it's a very simple indicator of weather conditions and how the weather conditions may be changing. All right, we still use barometers, you guys, even to today. Weather reports still record atmospheric pressure. although we no longer use a great big pool of mercury, which is what Torricelli did. He basically had this bowl that would be full of mercury, and there was a column of mercury inside of a glass tube, and then he could basically read the level of that column from day to day and see how pressure was changing. We'll go more into that in just a moment. So simply explained, we're going to talk a little bit about that barometer of Torricelli's that's really still in use today, although I'll be honest with you, we actually use electronic measurements now, pressure sensors, instead of an actual barometer. So the first question I would ask is, why use mercury? It seems like kind of a pain to have to utilize mercury. Mercury vapor is poisonous. So why use mercury instead of water? Water would seem like a much easier material to use. Well, here's the problem with water. As we go through this, you guys are gonna find out that basically to have the same water pressure that we get from air, you would have to have 33 feet of water. All right, so to basically have the same pressure from that big tall column of water that you would get from the air pressing on us right now, you would actually have to have a 33-foot column of water. So every weather station that you would have if you used water would be a little more than 33 feet tall, like 3 stories it would have to be. And that's just not practical. But by using a more dense fluid like mercury, what you're going to find is that you don't need as tall a column. So while your water column would be 33 feet high, if it's mercury, it's only about 30 inches high. So much more usable in terms of making those measurements of pressure. So this is all about being able to utilize a device like a barometer, and just 33 feet is way, way, way too tall. So to understand how this barometer functions, you have to realize that pressure is essentially a force, and that, like any force, the air pressure can actually move objects, including that mercury. All right? So what ends up happening here is that if you look at this diagram, air pressure from the atmosphere is going to push down on the surface of this mercury here that's underneath the tube that's going to measure our pressure. Now, like all fluids, and mercury is a fluid, it's a liquid at room temperature, if you exert a pressure on one part of the fluid, all right, what we've found is that that pressure is translated throughout the fluid. This is the way that your car brakes work. When you push down on your brakes in your car, it's going to compress some fluid, or try to compress fluid, which is your brake fluid. And then that pressure that you put on the brake fluid is translated to the wheels around your car. All right, so it's a way of moving force, I guess you could say. So in this case, what would happen is you would, to set up a barometer like this, you would do just like you did with your cup in the pool. You would fill this entire tube with mercury, okay? There would be no airspace at the top of it, because essentially this thing would be flipped right side up, where the open side here is actually upward. You'd fill the whole thing with mercury, and then while you hold your finger over the bottom of that tube, you would very quickly invert it, flip it over into a large pool of mercury like we see right here. So this would be there already. You'd flip this tube over so that it went into the mercury. So what happens then is all the mercury that's inside of the tube tries to move downward. Gravity's pulling it down, all right? Now, as it pulls down, of course, the amount that pulls down and then goes out into this pool that's on the bottom leaves a vacuum at the top. There is no air in this space because that space was formerly occupied by mercury. So what's going to end up happening? Well, gravity is going to continue to pull downward, right? Gravity is pulling downward on this column of mercury, but air pressure from the atmosphere is pushing downward on this, and that's translated upward. Now, what can you say if this line right here doesn't change, the level of the mercury, I mean, if that line does not move, that basically means that the downward force due to gravity, the weight of that mercury pulling downward, must be equal but opposite to the force generated by air pressure going upward. All right, so again, that air pressure pushes down here, that's translated upward inside the tube. Gravity is pulling downward, and we know they're equal because the level of the mercury doesn't change. So at sea level, guys, your height of a mercury column at sea level would be 29.92 inches. All right. If you have a barometer and you have the average sea level pressure, that level, that height of mercury above the bottom, the pool here, the measurement from here up to here would be 29.92 inches. Or if we convert this into millimeters, which is more commonly used, at least everywhere but the United States, this would be 760 millimeters of mercury. So at sea level, you would have a mercury column of 760 mmHg. All right, that is one way to measure pressure. Now, let's say a storm's coming. If you have inclement weather, you got a storm coming, typically what happens is the pressure outside drops. So that means instead of pressing down with the pressure that we had before here, the atmosphere is going to push down with less pressure, which means less pressure going up the tube, and the weight of this stuff doesn't really change. So now the weight of this column of mercury is greater than the atmospheric pressure pushing back up. That means this level is going to fall a little bit until the weight that's left in this column equals the new pressure. So you would see this level just drop down a little bit. If you had a high pressure moving in, you'd see the exact opposite. The air is going to push harder on the surface of the mercury, which means a greater force pushing up this tube, and it would be greater than the weight of the mercury in the tube. So that would force that mercury upward. So this level would change and get a little bit higher until that weight again equaled the air pressure pushing upward. This is basically how a barometer functions. All right. So what would happen if that vacuum that we have here, what happens if this is lost? So we have a hole that's in our tube, let's say, on the top. Well, in that case, if you think about it, you would have the same air pressure pushing on this pool and going up the tube. If you had a hole in this tube, you'd have the same pressure pushing downward on the surface. And so you no longer, these two forces, the one going up the tube and the one actually coming from the atmosphere and pushing down on the mercury, would be equal, but in opposite direction. So now the only force you would have acting on that mercury is weight. And that would push that mercury right down into the pool where it would stay. So the whole tube would empty out. Effectively, you guys do the same thing. If you have that cup in the swimming pool and you lift it up until it's almost above the water and then finally do go above the water. Soon as you do that, you no longer have the air pressure pushing down on the pool and forcing that water up into the cup, and all the water drains out of the cup. All right. So this is basically, you guys, how we measure pressure. Remember that pressure is created due to collisions between gas molecules and the container that they happen to be in. All right. So we're going to talk a little bit more about manometers instead of barometers, but we'll go over into that too. And then we're going to look at some pressure units and pressure conversions for this first section in chapter 5. Okay, we talked a little bit about the way that a barometer works. And remember that a barometer is simply measuring atmospheric pressure. The pressure that we get due to the fact that particles of the air around us are colliding with us all the time. So, as we said with the barometer, you have an atmospheric pressure that's pushing down on that surface of the mercury. And then because of the way that pressure works, that force that's generated by atmospheric pressure is then translated up the tube. Okay, again, this is the way that pressure functions. We utilize, for instance, we use a fluid in our cars that allow our brakes to function. And so by stepping on the brake pedal, you're compressing, or at least trying to compress, your brake fluid. That pressure is then sent throughout the brake lines and actually makes the brakes close. So that's how we stop. So this pressure is actually, when you think about how it's acting on the mercury that's in this tube, that pressure is going upward. But going against that pressure is the weight of that mercury. And so that is actually going downward. So the combination of these two forces, one pushing up, one pushing down, is going to give me my height of that mercury. So the height of that mercury is going to be a certain value. I'm going to get rid of that. That height of that mercury is going to be a certain value. Now, if you think about this, we use barometers to predict weather. And so if the pressure outside drops, it doesn't push up so much, but you still got that same weight of mercury in there. And so that weight is going to pull this level of mercury down a bit when atmospheric pressure is lower until it equalizes again. So you'll see this level drop. If pressure's high, like when it's not stormy or anything, you get more pressure pushing upward, which means it's gonna push more upward than this weight pulls downward, and it's going to increase the length of this column until the weight again equalizes the pressure. So that's how we measure atmospheric pressure. Now, if we're dealing with a pressure of an enclosed sample of gas, so let's say you did an experiment or something and you captured a bunch of CO2, okay? And we've got that CO2 and it's trapped inside of a glass container. Typically, those containers would have a valve on it so you could close it. And then you'd hook it up to something called a manometer. All right, and a manometer kind of uses the same idea, but it's set up just a little bit different. What the manometer uses is it's going to have an open end on this end of the tube. And so it is open to atmospheric pressure, which is going to enter the tube and press downward on that surface of the mercury. So the mercury here would be pressed down on by atmospheric pressure. Okay? If we open that valve and allow the pressure that's inside of here to come out, so I'll just write pressure. All right? That pressure is going to come through here and push down on this side. Now, if you had the configuration that you're seeing right now on this drawing, I would basically say that the pressure of the enclosed gas sample would be equal to atmospheric pressure. What allows me to say that? Well, if I look at these two levels, they're equal to each other. So that means the atmospheric pressure must be pushing downward on this side with the same force that the gas sample is pushing downward on this side. Now, on the other hand, let's just say, I'll kind of move these around a bit. See if I can erase this without totally messing it up. All right, let's say that we have something that looks more like this, a setup that looks more like this. So that's kind of the upper edge of where the mercury is here. And on this side, it's been pushed downward. So it looks like this. Get rid of my little red line. So let's say we have something that looks more like this. Well, now what I would say, and if you kind of look at this for a second, they're figured out in your own mind, which pressure is going to be greater? Is the enclosed gas pressure going to be greater, or is atmospheric pressure going to be greater? Well, what I would say here is, because this mercury was forced up this tube, it was pushed down on this side more than it was pushed down on this side, forcing it up that tube. So in this case, what I would say is that the pressure, I'll say, of the CO2, in this case, is going to be greater than the pressure of the atmosphere. Okay? If I reverse the two, if this one was lower and this one was higher, clearly atmospheric would have been greater. So is there a way I could actually figure out what pressure that sample had? It's pretty simple. All I really have to know is that the pressure of the sample is equal to the atmospheric pressure. And I'm going to say plus or minus right now the pressure difference, let's say. Okay, how am I going to get the pressure difference? Well, all you have to do is look at the difference in heights. If I look at this one and drew a line straight across here and a line straight across here, I can see that there's a difference in height between these two columns, and that would be measured in mmHg. So I would have a certain number of millimeters of mercury difference here. So let's just say, for argument's sake, that your atmospheric pressure on this particular day is 762 mmHg. Okay? How would I know this pressure? Well, these days, you could have a gauge that measures pressure. You could check your weather report for your local town. So Imperial, if you got online, you could check it and see what it was. Or you just have a barometer sitting around, and you utilize a barometer to measure that pressure. But you've got to have atmospheric pressure to know what the pressure of the sample is. Then all I do is I either add or subtract the difference. So let's just say, for argument's sake, that the difference in height here is 15 millimeters of mercury, okay? So to get the pressure of your actual sample, I would take my atmospheric pressure, which is 762 mmHg. Now the question is, do I add it or do I subtract it? Here we need to use just a little bit of logic. We know, if we look at the manometer, that atmospheric pressure is less in this configuration than the enclosed gas sample was. Again, how do I know? Because the enclosed gas sample pushed this side down against atmospheric pressure, so it must have been greater than atmospheric was. So that means my pressure of that gas sample must be bigger than atmospheric pressure. That means I must add that difference. So I'm going to say plus 15 mmHg. You guys can see this is not a real difficult question here. So if I add 762 and 15, this would give me 777, I think is what it is. Yeah, mmHg. So that would be the pressure that was inside of this container. And again, remember, if these were flipped, if this one was lower than this one, that would mean atmospheric pressure would have been greater than this enclosed gas pressure. And instead of adding that 15, I would have subtracted it. Okay? So you kind of have to be aware of which pressure is going to be, greater. And that's going to help you know whether you need to add or subtract those. All right? So this is barometers and manometers, kind of showing you how you can get a pressure from this. Next up, we're going to look at some units of pressure and how to do pressure conversions. Cut. So if we think about units of pressure, what would make the most sense if you're measuring pressure using a column of mercury is to use the height of that column. And so one of the first units that they really came up with to measure gas pressure is millimeters of mercury. All right, so we're measuring the height of a mercury column to tell us what the pressure is. So mmHg was one of the first units that we used to measure pressure. Now, you also kind of want to have a standard. I mean, what height should I call the standard pressure? Well, that's going to be the height that you would typically see at sea level. Remember that gas pressure, as you move upward in altitude, gas pressure gets lower and lower and lower because you have fewer and fewer and fewer gas molecules around you that would impact you every moment. So fewer molecules means less pressure. So what they decided on was, let's use sea level. And so what you see, I'm going to write down a bunch of equivalent pressures here, but with different units. They decided what the standard pressure was going to be would be 760 mmHg. Now, I guess the Italians got mad or something. I don't know. They wanted to honor Torricelli with a unit. So what they said is, how about if we call an mmHg, or 1 millimeter of mercury, we're going to say that we're going to call that a torr. So they also said that 760 mmHg would be equivalent to 760 torr. Thankfully for us, they didn't call it a Torricelli, they called it a torr. So if you have 1 mmHg, you have 1 torr. They're equivalent to each other. We couldn't leave well enough alone. We decided we wanted some more units. And so what we would say is that this would be equivalent to 1 ATM, or atmosphere. All right, so I'll just kind of put that in parentheses. So 760 torr, or 760 mmHg, is equivalent to 1 ATM, or 1 atmosphere. Then the folks came along with SI, the metric system, and they decided they wanted to use a different unit for this because this wasn't really based on anything horribly logical, except it's at sea level pressure. So they decided they wanted a different unit. And I'm going to go ahead and write that one down here, but know this, that the units I'm going to write down here are equivalent to these. So they used a unit called a Pascal, all right, or a PA. And this is 101,325 pascals. And again, what a Pascal is, you guys, because if I look at this, I say this doesn't make any sense. But this actually would be a unit that we would use in the metric system, because this is a Newton, a unit of force, divided by meters squared. All right, so we're using here those metric units, okay? Couldn't leave well enough alone there either, because this seemed like a really big number. So what if we called, instead of a Pascal, we call this a kilo Pascal? Well, remember that the prefix kilo means 1,000. So if I've got 1 kilopascal, I would have 1,000 pascals. So if I convert that to this, I would just move the decimal point. So it no longer is a comma. It's not 101,000. It's 101.325 kilopascals. Okay. Then finally, one more, and this is for us good old Americans. We would rather measure pressure in a unit that we see here, which is a PSI, or pounds per inch square. So PSI is pounds per square inch is what this stands for. And our number is 14.7 PSI. All right. So effectively what you have here is a whole bunch of pressures that are all equivalent to exactly the same thing. They're all equivalent to the standard atmospheric pressure that we have here on Earth. So lastly, as we talk about pressure here, I want to go over an example for a simple conversion. These really aren't too complex as long as you know what these values are that you're converting between. So I have an example of a question here. It says that you measure a pressure of 49 torr. What is this pressure in ATMs and in pascals? So anytime that you're doing a conversion problem, you always start them the same way. You write what you know. So the one thing that I know is that I have 49 torr. Then what I generally do is I'll ask, well, where am I going? Where do I want to end up at? And really, this is asking me two questions. So I'll tackle the first one first, which is it wants to know how many ATMs that is. All right. So I don't have what I want. In that case, a time sign and a fraction bar is automatic. Okay. I'm putting torr on the bottom so I can get rid of it. I'm putting ATMs on the top because that's what I want to end up with. And now I'm just going to use my numbers that are here to help me make this conversion. So I know that for every 760 torr, I'm going to have one ATM. Okay? Cancel your units. I can see that I have what I want. So I can go ahead and go to the calculator. And to do this calculation then, all I really need to do is divide 49 by 760. So let me get this to where I got my calculator going. 49 divided by 760 gives me 0.06 and the next digit was 4 and it was 6447. So I'm going to call this 0.064 ATM. Again, this value has 2 sig figs, just like the 2 sig figs that I was allowed in the question itself. To do the second part to this, I do it exactly the same way. Write what I know. Now, instead of atmospheres, I want pascals or PA. Don't have what I want, so it's a time sign and a fraction bar. Torr on the bottom again, I'd like to get rid of it. And I want to end up with pascals. Again, as long as I have some equivalence between pascals and torr, which I have up here, I should be able to convert this. I know that for every 760 torr, there is 101,325 or 101,325 pascal. All right. So if I cancel my units, I can see that it's in pascal, which is exactly what I wanted. And thank goodness for calculators, so we don't have to do too much math. But I'm going to say 49 times 101,325. I get a big number, like 4.9 million. Then I'm dividing by 760. And I get 6,533 pascal. But this has too many sig figs. So I actually would round this to 6,500 pascal. Again, with no decimal point, because if I put a decimal on it, those zeros count. So your two conversions, again, they're like every conversion that you'll ever do. Your two conversions here, write what you know, write what you want, use a conversion factor, and remember that one ATM here is equivalent to 760 torr. So every conversion factor, you have a value divided by the same value essentially. And so what I'm really doing here, if you think about this, this is equivalent to 1. So I can multiply this number times that number, and I really haven't changed the amount of pressure. I've just changed the units. All right. So those are conversions, folks. You're going to get a little bit of work on this, and that'll do it for pretty much for the pressure section. But we will be continuing to use pressure as we go forward. So don't forget how to do this stuff. All right. We'll see you next time.